Section 5.4 is about the Fundamental Theorem of Calculus. I give it an important sounding name because it's pretty important stuff. We've already seen the first half of the Fundamental Theorem. In 5.3 we saw the evaluation theorem. So now we're looking at this other half, which is the accumulation function part. Fundamental Theorem of Calculus is all about definite integrals. So here we see a definite integral. And of course we've already learned definite integrals give us areas under curves, and you evaluate it from A to B. Wait, that's not a B, that's an X now. Hey, they did that on purpose. So if I evaluate the area under a curve from a number to a number, from a fixed actual area, it's going to give me a number answer. But if I evaluate from A to, I don't know, sometimes it's going to be this number, sometimes it's going to be that number. If I vary the right-hand edge, I'm going to get different answers out. And that's what functions are, right? If you vary the input, the output gets varied also. So here's my function, g of x. Depending on what gets put in this upper spot, I'll get out different areas. So that's not the cool thing. Defining this function isn't the cool thing of the fundamental theorem. The cool thing happens when you look at the derivative of the accumulation function. And this theorem establishes that the derivative of this integral is the original function itself, f of x. There's some little trickery where you're swapping the t in the integrand for the x that is the variable of the function, but that's easy to do. Now, speaking of the variables in this problem, in the box, to use the fundamental theorem of calculus, it's really important that the variable x is exactly what is in the upper spot of the bounds of integration. If you look at the problem 13 that I've picked, that's not the case. So here they're asking us to find the derivative, and that upper thing isn't the variable like we're expecting. Instead, it's a function of that variable. Well, where else in calculus have we seen, here's some rules what to do with x. Oh wait, now instead of x, I'm going to put a whole function in that spot. This comes up when we do the chain rule, and we're going to use the chain rule again here to solve this problem. So this problem is really similar to example 5 from the textbook, and we're going to use the Fundamental Theorem of Calculus Part 1 along with the chain rule to solve it. So recall the chain rule. What was that from calculus? Here I've got it written in Leibniz notation, but essentially you're going to think of the function that you're trying to take the derivative of as having an outside and an inside. It's a composite function. And so in order to take the derivative of the whole thing, you take the derivative of the outside function and you leave the inside alone, so derivative of the outside with respect to the inside, and then you come back and you multiply by the derivative of the inside function, and that's with respect to the original variable. So what does that mean in the context of our problem? We want to take the derivative of h of x in our problem with respect to its variable, which is x. So the chain rule of that would be dh dx equals dh du times du dx. That's just rewriting the chain rule in terms of the variables given to us in our problem. Now, our variables also don't exactly match the variables in the statement of the fundamental theorem. So let's come back and rewrite the statement of the fundamental theorem in terms of our variables. So I've got here this function, the integrand is arctan t dt, and the upper bound of integration, I'm going to let that be u, because that's my inside function. I don't like it being a function, so I'm going to use the variable u to represent it. And a can be any number, in our case it's 2. And now instead of g of x here, they called it h already, so let's call it h. It's a function of u, because we want the variable to be the one that's represented as the upper bound of this integration. So the fundamental theorem tells us once I have it written this way, where the u's match, the variables match, then the derivative of that accumulation function, see here g prime, the derivative of our h, dh du, is equal to the integrand where we plug in the variable. And here my variable is u, my integrand is arctan t, so I have that the derivative of h with respect to u is arctan u. This is what the fundamental theorem gives us. To solve my original problem where I want dh dx, in addition to dh du, I'm also going to need to find du dx. So here, what was u? U was 1 over x. Rewriting, that could be x to the negative 1. So the derivative of that, and that's just a power rule. Bring down your negative 1 to the front, so I have a negative, and the power goes down by 1, so negative 2 in the derivative. The derivative du dx is negative 1 over x squared. So we put these together, and I get that dh dx is dh du times du dx. dh du up here was arctan u, and du dx is negative 1 over x squared. And then, of course, we don't want to leave our answer in terms of u, so I go in and plug back in that u is 1 over x, and I just flip-flop the order because I like to see this fraction in front of the arctan. And we're done. But I'll admit that my answer doesn't look like the way the book worked out example 5. So if I wanted to write the same solution differently, just kind of saying it in different symbols, same words, different symbols, I could talk about the derivative of the whole thing, the composite function, equals the derivative of the outside function with respect to u, that leaving the inside function alone, here, see the u's match, times the derivative of the inside function with respect to the original variable. So this is by the chain rule. This is what allows us to write it out this way, and I'm letting u equal 1 over x in order to do so. In this case, the fundamental theorem of calculus part 1 applies just to this little spot right here, this part, and it tells us that the derivative of the definite integral is the integrand evaluated at the variable, which is u here, so arctan u, and then times du dx. I haven't handled that part yet. And then I go and I finish everything up and plug in my 1 over x for u, and of course du dx I already figured out up here is still negative 1 over x squared. So that's my final answer, same as the final answer we got up here. They match, and two different ways of writing up the same work in a problem. Thanks.